How is this all relevant? And in particular, what's the relationship between this story and the concept of a sample variance? So the final stage, final point to cover is to look at sample variance and how these expectations help to explain maybe what's a mystery. So we're going to talk about the relationship or the relevance to sample variance. So just to recall, the sample variance, it's a definition you should be familiar with. Sample variance is equal to the sum of each observation minus the average squared, added up, and very often we divide that quantity by n minus 1. And very often people say, well, why are we dividing by n minus 1 here? Surely we're talking about an average. Much better to divide by n, because we've got n terms here. Why don't we just divide by n? And so the question then arises, well, should we divide by n or n minus 1? And I'm going to explain through the concept of these expectations why this n minus 1 is the right thing to do for most purposes. But in order to do that, I want to go back to our concept of random variables. Instead of looking at data, which are little values of x, consider the random variable with a capital X. So let's just try and keep things not too complicated or messy. Is just to consider, first of all, xi minus x bar squared, I equals 1 to n. Okay, so instead of using the lowercase x, this is for a sample of data, I'm going back to capital X's. So these are random variables which have their distributions, their sample spaces, and so on. Okay, so this is a sum of a bunch of different terms, and we'll just consider the first term. So the first term in the summation is going to be x1 minus x bar squared. Okay, so we take x1 minus x bar squared plus x2 minus x bar squared, and so on. And we can expand that, and this is one of those cases where after you know the answer, you can see how best to write it down. And at first it's a mystery of why this is right, but you'll see how it comes out. So what we're going to do is simply subtract mu inside that bracket, but then add it on again. And so when I add it on again, I can imagine two terms. Okay, so this is x1 minus mu minus minus mu, so the mu's disappear, and then we have x1 minus x bar, which is what we have on the left-hand side. And the reason for doing that is we now treat this as, if you like, two terms. So this is the first term and the second term, which we square. And so we have the first term squared minus 2 times the cross product. And then we have the second term squared. Okay, so all I've done is take these two terms here and treated them as, like, if you like, a plus a minus b squared, so a minus 2ab plus b squared. Okay, so now we're going to take expectations. So on the left-hand side, we have the expected value of x1 minus x bar squared. On the right-hand side, we can look at these various quantities. This is the expected value of x1 minus mu squared, and that's just the definition of the variance. So that's the variance of x1. The next term is a bit messy. Well, let's just try and unpick a bit of it. So we have 2 times the expected value, and now I'm going to multiply out what's inside. And you may have to just check the details on a bit of paper yourself, but we have x1 x bar minus mu x bar minus mu x1 plus mu squared. And then the last term, this is exactly the variance of x bar. because x bar has expected value mu, and the definition of a variance is the expected value of a random variable minus its expectation squared, and so that's just the variance of x bar. So we've gone from something quite simple to something a bit more complicated, and the middle term here still requires more work, but the end terms we've extracted out, and they're now looking very simple. So in particular, the first term is just sigma squared, and then a little bit of care, because x1 appears here and inside x bar, so when we multiply that out, we have to worry about whether x1 is in x bar or not, and we use, if you like, the notion of independent variables here, and so this is just the variance of x1 plus mu squared plus n minus 1 mu squared, bracket there, minus mu squared, plus the variance of this we've already shown to be sigma squared over n. Okay, so now we're nearly there, because we've got the variance of x1, we already know that. If you look at the mu squareds here, we've got plus mu squared, minus mu squared, they cancel out. Then we have n mu squared divided by n, so that's just mu squared, so that cancels with that one. So this middle bit here is very simple. So we have sigma squared minus 2 over n times the variance of x1, which is sigma squared, and then the last term is sigma squared over n. So that simplifies again. We can write that as sigma squared times n minus 1 over n. Okay, so now we have this quantity here we're trying to look at. We've taken the first term out of that sum, and we've shown the expected value of that first term is given by this. And you notice that doesn't depend on the index here, the 1. And fairly easy to see, if I'd substituted, rather than looking at the first term, I looked at the second term and took x2, there's nothing to stop it being exactly the same answer at the end. So all n terms in this summation have the same expected value, and because there are n of them, we can just multiply that by n, and we finally have then, let's put a hence if you like, the expected value of this sum is equal to n of those, which is n minus 1 times sigma squared. So this is our expected value of that quantity, and that means, this is, if you like, the crunch line. Finally, we have the expected value of the sample variance, where we're substituting in now random variables, is equal to the variance that we want. Okay, so there's the mystery, if you like, solved of why we have n minus 1 here, is because only by substituting n minus 1 do we end up with a value. If you think of the sample variance as trying to estimate a population variance, we're saying that if we use n minus 1, the expected value for our sample variance from a random sample is equal to the population variance. Now, of course, if n is large, this is going to be about the same whether you use n or n minus 1. But certainly for smaller samples, it does make a difference, and it's worth getting it right. And that explains why that should be the case.